Hello, this is Dr. Scott Friedman, and I'm pleased to introduce to you the topic of my focus feature for the March issue of Journal of Hepatology. The theme of my article concerns the telomere, the end of chromosomes that has become an incredibly interesting area of science, so much so that it earned the Nobel Prize in 2009 for investigators who linked telomere erosion to the emergence of cancer and cellular senescence. The two papers I'd like to review briefly are by Aravinthan and Verdam that both address non-alcoholic steatohepatitis and fatty liver disease. In the first paper by Aravinthan, they examined the length of telomeres in patients with progressive liver disease due to non-alcoholic steatohepatitis. And using molecular and biochemical methods, they were able to demonstrate that telomeres become progressively eroded as liver disease advances in this condition. As these telomere erosion advances, the cells become increasingly incapable of regenerating and show evidence of DNA damage. What that means is that as non-alcoholic steatohepatitis progresses inexorably to more advanced disease with fibrosis and cirrhosis, there are events occurring at the end of chromosomes that trigger cell cycle arrest and impair regeneration. One wonders whether that decreased regeneration somehow elicits a more fibrogenic response, or possibly that increased fibrogenesis associated with inflammation and fibrosis also contributes to impaired regeneration. In addition, there's other evidence that suggests that telomere shortening is linked to mitochondrial damage, which has also been implicated in non-alcoholic steatohepatitis. And so what's beginning to emerge both in NASH, but more broadly in many chronic inflammatory liver diseases of the liver and elsewhere, is the fact that progressive disease is associated with progressive shortening of the ends of chromosomes, and this elicits a DNA damage response that not only impairs cell growth, but may ultimately sow the seeds for the emergence of cancer. So stay tuned in this exciting area for further studies looking at telomere biology and their link to clinical liver disease. The second paper by Van Dam from the Netherlands introduces a very interesting diagnostic technique to potentially distinguish fatty liver disease without inflammation from non-alcoholic steatohepatitis. They do this by using a method to measure organic volatile compounds that are excreted in the breath. And using sensitive biochemical techniques, they have shown that the patterns of these organic compounds changes as progressive fatty liver disease becomes non-alcoholic steatohepatitis. Or more specifically, that those patients who have bland steatosis have a different pattern of excreted or exhaled organic ions than those who have non-alcoholic steatohepatitis. The receiver operating characteristic was 0.77, which is good but not fantastic. On the other hand, we really have very few methods, if any, to really reliably distinguish patients who have bland fatty liver from those who have steatohepatitis. So this test, while certainly not readily available widely and while needing to be validated by other groups, still introduces the concept that there may be non-invasive methods of detection that can distinguish fatty liver disease from non-alcoholic steatohepatitis. Now, this isn't the first method to attempt such an approach. There are, in fact, several breath tests that have been developed, including the MEG-X, the caffeine elimination test, and methacetin breath test, all of which rely on the liver's ability to either excrete or possibly metabolize substrates, and the speed with which those substrates are metabolized in some way reflects the underlying state of the liver. So this study, while somewhat early in terms of the technology, nonetheless represents an important new direction in trying to establish breath tests or non-invasive tests of any type to help uncover the state of liver disease and to avoid the need for biopsy or other non-invasive methods.